we have with us Professor Douglas Vandemark. He is a faculty from UNH working at the Institute for the Study of Earth and Ocean Science. He did his Bachelor's of Science from Hope College, Master's of Science from UMass Amherst, and his PhD in Earth Sciences and Oceanography from UNH. His research interests lie mainly on AC interaction with focus on remote sensing of wind waves, exchange of momentum, heat, and nets. And today, he's going to talk about autonomous AC mass flux, more in sync with AC interaction stuff. So, take it away.
All right, thank you very much. Thanks for having me. I think I can see who is holding the captive audience here. But for me, it's great to be here on Friday afternoon because I know it's Friday afternoon. The week is almost over, so thank you for being here on such a beautiful day. And the topic I'm going to talk to you about is up there. I didn't want to gloss over this slide like I usually do, just to make sure that I remember to say multiple times that this is a team project. The people that are listed down there are contributing, I would say, much more than me. I'd like to say that I helped to bring this group together and hold them together for some of the, as I'll explain over the course of the talk a little bit, but locally, if you haven't run into Sean Shelato, I hope you get a chance and you get to go out on the Challenger with him and do something interesting. We're always looking for somebody to go out on the boat with us. So if you are interested in getting out on the sea locally, Sean is a great guy to contact, and Mark is the project engineer running this project. And just to briefly introduce myself a little bit more, I know UNH and oceanography can be a little bit confusing in terms of where we all are and what we're all doing. I work for the Ocean Process Analysis Lab over at EOS, and this is in Morse Hall, and this is just some of the ragtag group that's part of our lab. We're one of the founding labs of the Institute for the Study of Earth, Oceans, and Space. And I think this is our 45th anniversary. The lab was started in 1980, and I was a founding member. No, maybe. No, I came about 20 years ago. But our director is Kai Ziervogel, and maybe you recognize some of the faculty here teaching class. And this isn't all of us, but this is a little sense of it. And we work across a range of oceanographic topics. It's a research-intensive oceanography group. And so that's kind of where I sit. And in my particular case, we won't show this again, but we will. Is I work coming from the topic of satellite remote sensing. Is my background. I have a radar engineering degree, was my first degree, and what I spent a lot of years working at before I came to UNH and moved into oceanography. We work across the range of satellite observing systems that look mostly at the ocean surface. And so I'm very interested in the ocean surface, have been for a long time. I know a lot of you guys are bottom mappers. It's going to be a surface talk. And in terms of projects, I typically, our group, my team with Mark and Sean and a couple others, typically have 10 or 12 projects going on. And so it's always interesting. Tom says, hey, tell us what you're doing. And I'm like, well, okay, so I chose one. So, but we're working right now across a range of products with wind and waves. And a lot of this translates into weather forecasting. We're really into atmospheric boundary layer mapping at the global scale right now. And there's a new NASA mission SWAT that we're spending a lot of time on. That's an interesting hydrology, high resolution ocean mapping mission. The one that we'll be talking about today is a topic that I was interested to work on when I moved to UNH quite some time ago, and I'm still trying. And so that's what this talk is sort of about. We're interested in looking at EC CO2 flux. And one of the reasons we get into this is part of what goes on in our lab, and that I oversee right now quite a bit of this, is we've been making ocean observing measurements in the Gulf of Maine, and sometimes in support of the satellite measurements, sometimes locally for the Weather Service, using a range of buoy systems. I think we have 4 or 5, I guess 6 time series stations running right now across the near shore and the Great Bay out to Jeffrey's Ledge. Part of this gets us into the capability to be making measurements in situ out in the ocean. And so we're able to put buoys out that do research grade work as well as monitoring work. And one of those has been carbon dioxide measurements since 2006. So we're almost to a 20-year time series in the Gulf of Maine of ocean carbon dioxide that's part of a national network. And I think we're the oldest node in it. And so this brings me back to the focus for this talk, which is we're trying to develop the capability to actually monitor carbon dioxide coming in and out of the ocean surface with a precise measurement system. And in order to do that, I'm going to work through some of the technology of that in this talk. But we've had 2 projects funded by the National Science Foundation. The first one, as I stated up here, was basically a technology effort where we're interested in why the measurement has been so difficult for so long that we're trying to do, and see if we can figure out how to fix it and demonstrate the problem that many scientists that have been trying to make this measurement in the field for quite some time have come across. And that project ended a couple of years ago, and I'll kind of give you an update on where that was. And that led into the project that we're involved in now from the same program, which is to improve on what we did last time and get to a place where we don't only know how to do it, but that we're going to make something commercially available to the community. And so part of that effort has been basically developing a really good partnership with one particular vendor as part of this effort. And so to get back to what I said about why we want to measure this, this is a busy slide that I'll spend some time on, but I thought maybe the most dramatic way to illustrate this is, with some kind of carbonated beverage. We're basically trying to keep track of the exchange of carbon dioxide between one reservoir and another, in this case, the atmosphere and the ocean. And it's obviously a greenhouse gas, and it's of interest to many sciences on many time scales. And in the case of the ocean is sort of the flywheel on the planetary scale for greenhouse gas exchange. Because it's so large, it's such a large reservoir of water, it basically, for example, is modulating or moderating 30% of the fossil fuel emissions. They go into the ocean. And typically, the process is very slow and it's very small, and that's part of why we are struggling to make this measurement. But over 100,000-year time scale, the ocean is what's in control of greenhouse gases in the end, to a large extent. And so what needs to be understood about the exchange of carbon dioxide between the atmosphere and the ocean is this term F up here on the far left. And that's basically the rate of exchange. This is molecules of carbon dioxide per meter squared for some time. And this is the quantity that needs to be estimated, for example, if you're doing some sort of manipulation of the ocean and you're doing this marine carbon dioxide removal, where companies are trying to sink carbon dioxide right now into the ocean. If you're trying to model climate prediction at 10, 20, 30, 40, 50-year time scale, or go backwards. this quantity is, if you don't know it accurately, you really start to get uncertainty in your estimate of the basic carbon and how it's moving between the atmosphere and the ocean. And there's a couple ways that this is measured. This isn't all of them, but two of the ways it's measured is that middle equation is a turbulent transport equation, where we actually, this is what you would call the most direct measurement, eddy correlation. And if you've taken Nathan's class, you'll know this very well. This is the way that you would like to measure an exchange across this interface of the sea surface. And what these prime quantities are here, one is the vertical velocity, and we're just doing a Reynolds decomposition to get to the prime. And so you'll take typically a 10 or 20 minute average of the vertical velocity of the wind, and then you'll leave on the table what you're after is just the deviation from that. And these are very small vertical wind deviations that are typically associated with eddies in the atmosphere of different scales. And then what you do is you do the same thing with carbon dioxide. And when you put the two together, if you've got carbon dioxide increase and you've got a velocity increase, you're going to be ejecting carbon dioxide and vice versa. So over 20 minutes, you do this accounting of this measurement. We typically like to make this about 20 times a second in order to capture all the eddies. And this is a very, very small quantity in both cases, the vertical velocity and the CO2 perturbation. And this is the whole issue of how well can we make this at sea on different platforms. And that's what this project is essentially about. And where it ends up going is in this equation on the right. This is the one that the climate scientists use. This is the one most people use. This is the one I use because it's very seldom that you can make a measurement at 20 hertz out over the ocean accurately. In fact, if we can discuss, hopefully I'll get to it, it's done very rarely and very rarely is it done well. So you're left with a more scalar equation. And that's the equation on the right, where the differential between the atmosphere and the ocean carbon dioxide is known as a delta PCO2. And this typically changes in the ocean at a fairly slow time scale, like 10 minutes, 30 minutes a day. The atmosphere can change quicker. Like, for example, right now, if we still have photosynthesis, these trees are sucking carbon dioxide out of the air. So during the day, the atmospheric CO2 is about 10-15% lower than it is at night when it's respiring back out. And we can see this out at Appledore Island. You can just watch the forest of New England taking the CO2 up and down in the atmosphere. It's pretty interesting. But the ocean's moving slower, but both of them we can measure fairly accurately. It's these perturbation terms that are tricky. And then on that equation on the right, the K term is what the information that we're trying to measure in the middle can help improve. And the K term is a catch-all. That's a scaling coefficient that is the rate of transfer as best you can do in a scalar equation. And it's typically just a function of wind speed. So all of the work that we're trying to do is to prove or disprove how well the K model is built right now. And that was a long-winded slide, but are there questions about this? I'm open to them. Sure.
With the K models, do they physically, when you're converting from flux per area to sort of total mass flux, the first equation, it seems like you can just use horizontal area. Yep. But with the K, determining K, do you need like the actual area perpendicular to the water surface, and so you have to account for area increased by waves, kind of, or is that incorporated in the empirical?
It's incorporated. In terms of all the physics that you might think might be affecting that transfer rate on a given day. There's a lot of processes that go on out there in terms of like sea spray, breaking waves, rain, etc. Maybe the area changes with the wave field, for example. We don't know how much, I shouldn't say we don't, people have tried to constrain the different physical processes that are going into the K-term. The issue is, how do you constrain it when you're not measuring it? And so they try to measure this middle term in the field and compare it to the K models that exist and the say a machine. Nowadays, if you had a lot of data, you'd do a machine learning model, right, to try to relate the two and figure it out. But the issue right now is we don't have a lot of well-conducted experiments where we have these other variables that we could put into that equation and assess how well they are. And there are theoretical and physical models for the K-term, and these are waiting to be tested as well. And so it's not that there isn't capability to look at the equation and its uncertainties. There's many papers written on it. It's just that the one thing that people are looking for is kind of a gold standard measurement to be able to go out and say, okay, we've got it, especially the more that carbon becomes a currency. Any other questions?
Yeah, sorry, real quick, Doug, thank you. The vertical profile of W prime XC prime.
Yeah.
Would that be the ideal measurement that you would be after? As difficult as it is to measure a single point.
Yeah, well, that's a good point. Anytime we're doing these kind of Reynolds stress measurements, we're typically doing them in a Eulerian sense at one particular height above what other medium we're looking at. This is in practicality because to do this at multiple heights just adds to the level of complexity. And there's a thing called the constant flux layer, which is typically thought to be of the order of around 80, 100 meters, depends on the height of the boundary layer, where we make the assumption that these eddies and their transport are more or less constant. And so placing this sensor anywhere within that layer should give you a similar answer. But in this case, because we're measuring stress or we're measuring turbulence, we're not so concerned with the vertical difference in where this measurement is made. There's another way to go about measuring the profile of these constituencies, but that doesn't get you really at the eddy turbulence part of the measurement.
Okay, great, thank you. Yeah, excellent.
Other questions? All right, so to go back to your question about the K term, I just threw up a fairly recent paper to try to illustrate a little more why we won't give up on trying to make this measurement. One of them is obviously how well does this transfer rate equation work, and that's the one most people are trying to answer. And just to say a little bit more about this, we had a meeting a couple years ago in London with a team of people that do this kind of work. It was a room maybe this size, maybe it was around this size. It was most of us. And it's not a big group, in part because it became so difficult, people just kind of gave up. But these guys, Ming, over at University College London, and he's really at the cutting edge of trying to do this well on a ship. And he's gone out on 15 cruises now. That's what shows up in this plot right here. 2,600 hours of measurements with a system like we're talking about, putting on the buoy. And he ends up from each of these cruises with around 100 to 200 valid data points. So these are hard-won data points out on a ship. When you think of 100 to 200 data points on a 2 or 3 week cruise, you can imagine you don't get that many differences in wave height and wind speed and the things that control the K term. And so you need basically tens of thousands, hundreds of thousands of data points to start to statistically do something better than what we have now. And so that's one of the difficulties he discusses in the paper. They have to throw out a lot of measurements, and they have to convince themselves that the 100 to 200 that they keep are good. And so it's an issue that people are hoping that we can make some improvement on. And so just to keep hammering on the problem, this is an example of what they do on these research ships. This is a mast on probably a 200-300 foot research vessel, instrumented across the mast with all kinds of sonic anemometers to measure these velocities. And then, it's probably hard to see, but these boxes are open path CO2 sensors to measure that concentration perturbation of carbon dioxide I was talking about. And you might ask, why do they have 4 of these? Why do they have 5 of these on the ship? And part of what they were trying to do was make a measurement of carbon dioxide that was a fixed reference. So they were flowing a tank of CO2 into one of these sensors, just measuring nothing, right? And then when the ship starts moving and heaving and everything, all of a sudden their measurements started moving and they're like, wait a minute, I'm measuring nothing, but it's telling me I have something. And that's basically, then they were trying to correct for this by saying, okay, this is what my system that is measuring a fixed rate of carbon, or a fixed quantity of carbon dioxide is doing. It's moving, but I'll correct my other data with this. So they were doing stuff like this it was not very, let's say, elegant, and it was also not working very well. And but people were trying everything they could because they wanted this measurement to be part of the program. And so we did this for a while with this buoy I'm showing you here, back maybe a decade ago, offshore in the Gulf of Maine, and tried to use the methods that these ship people were using to correct the data. And they called this their motion correction. So they were always saying, well, our measurement seems to be moving with the platform motion, whether it's a ship or whatever it was. When we went out on a buoy, we were like, wow, it's really moving. And it turned out, when we came back, we tried all the correction methods these people were using for the motion. So the error was correlated with the platform motion, and we can measure the motion very well with IMU packages, for example. What's shown here is a simple short time series plot of us in the lab just moving the sensor. And again, this is with a fixed carbon dioxide measurement flowing through the sensor at around 500 ppm. And the black is what is the noise of the sensor, the native noise of the sensor. When we started just moving it, we were getting these kind of changes. And so basically, partially because we destroyed this sensor because it got wrecked in a storm, we just took it apart. We just took the thing apart. These are, $10,000, $15,000 sensors, but you can't just call the vendor and say, hey, it doesn't work, because they really don't, that was a problem, is these vendors like Campbell Scientific and Lycor, they've got many customers and they also have proprietary information. So when you tell them your problem, sometimes they listen to you, sometimes they don't. But we couldn't get any engineers to talk with us about what might be going on. And so we just took it apart. And what we found was, basically these sensors look like this. You have a light bulb in this end, and you have an infrared detector in this end. And they modulate the transmit signal, and there's a timing involved so that they can make the measurement very fast. But essentially, the whole thing that we work for is what's between the transmitter and the receiver. There's a cell in here, it's a little bit of volume, and you do ideal gas law. So you're just looking for the pressure, the volume, the temperature, and you can get the number of moles of carbon dioxide that are inside this sensor at 20 hertz. It's flowing through here, you got fast rate change in carbon dioxide. So most people were thinking there was something going on in what they were doing wrong in the transmit end or in the electronics. And there would be a little discussion section at the end of the paper where they were waving their hands about their motion correction not working, and they think it was this and they think it was that. But finally, what we came to was in the detector, in the end, is a little infrared receiver. And they look like this. I don't know if you're familiar. This is called a TO3 can. It's a pretty small little piece of electronics. It usually drops in a circuit board. I think we're talking about half a centimeter across. And in there, that's a typical infrared detector, that little square. And then off to the left of it is a thermocouple. And these detectors need to be held at around -30°C to work well. So there's a thermoelectric cooler that's embedded behind the infrared sensor. It's built into it. And its job is to hold that temperature no matter what's going on out at the edge of the can. So the can could be on a hot day at the end of, in here somewhere, you could be at, say, +30°C. But that infrared detector has got to be held at -30. And what we found was that when we started manipulating it, it's like, oh, this is what's doing. And so the simple solution down here, after years of working on this and talking to engineers, was we needed to evacuate this detector. So they typically just fill this with nitrogen. When we evacuated it, the problem went away. And I guess I'm jumping to, we'll come back to this. I'm jumping now to all the hoops we have to jump through to keep the air that's flowing through this cell pure and pristine, and so that we can do our PV = nRT. And so in order to do all these things, we have to have a rather extensive system to pump the air from the top of the mast up there where that sonic mem is measuring the W prime and our XC prime, down into somewhere where we can package up all this equipment, where we basically dry the air, but also because we're out at sea, we have to make sure that we don't ingest any water. So if it's raining or we get sea spray and we get water in here, the experiment's over. And so basically I'm going to talk to you, hopefully if I speed up here a little bit, about the things that we have to do to make these things happen. This is a diagram of this sample conditioning of the air to get down to where we're making this measurement. And so as part of our program, we put an evacuated detector that I was just talking about into one of these sensors. We also went out with their standard sensor that you can buy off the shelf. And we put it on this buoy that I was showing earlier, and we put it out next to the carbon dioxide measurement buoy that we operate. And so this was in this first phase of the project. And these are the pieces of the puzzle as they went on to the buoy. And there's a busy plot up there that I'll show you on the next slide. But the take-home messages was that we showed that we could remove this motion correction issue. I would say 80–90% of it by changing the detector. And we were also able to develop a system to go onto a buoy, whereas you saw what they do on ships. They got lots of room, they got all the power, they can have a huge lab. We had to bring all this down into sizes that we could fit on a buoy. And so we were also able to do that as part of the project. But one of the things that NSF said to us, and they were right, is just because we can do it, so what? Because we got Campbell Scientific to build us one of these, and it wasn't they just did it quick. It gave us a lot of problems. So we knew the answer, but nobody can use it. And so part of the issue going out of this project was, yeah, okay, now we did this and we published our papers, but are we making much advance? So we'll come back to that. But this plot to just show you the results from that first experiment, the top plot is that thermoelectric cooler time series. And one of them is the stock unit you can buy from Campbell Scientific and put it on your buoy or your ship and go make a measurement. That's the blue curve. The red curve is the one we modified. So you can see that thermoelectric cooler doesn't need to do anything anymore because we evacuated the detector. It's a convective current inside that little can. So this is just buoyant convection of heat that was moving around in that tiny little can that it couldn't compensate for fast enough. And the spectra for the two is up on the right. But the bottom line from this plot was that we were able to basically clean up this motion by changing the detector. And I think the last time I talked to people at UNH, we couldn't talk about this because it was proprietary. And so now we have a patent filed for this, because this isn't only used in gas analysis. The laser systems use these kind of detectors in environmental science, military, things like this. So for a while we were going, hey, we fixed it, but we can't tell you why. But now that's done. And so now we're on to phase 2, which was the project we got funded once we got this commercial hookup better with Campbell Scientific. We went to NSF, they said, well, it's great, but no, we don't need to do this again unless you can give us something more. And so in this case, our idea was to do something better than they did last time. They did change the detector, but there were more things to improve on. We wanted to improve all these systems that I quickly ran through there about drying the air and preventing water ingest and getting the power down. And then the big part of our project was, can we come up with an approach that makes this, is there somebody that wants to build it, essentially? Because it's as I said, the room wasn't too big when we were in our flux measurement group. A lot of people are interested in this, but we couldn't convince Lycor or Campbell Scientific, who are the main vendors of this, that there was a business plan for this. But somehow we got lucky, and something happened, and I think it was the last administration in China where they just started buying these sensors by the hundreds, right? These gas analyzer sensors like this, and a market changed for observing. This measures both water vapor and carbon dioxide, and something changed in the market where Campbell Scientific just said, we'll work with you. And so what we've been able to do as part of this project now is we actually have 5 engineers from Campbell Scientific out in Utah that are working with us regularly. It's really enjoyable fun. And they came out here, and last November, we joined with them and went down to Woods Hole, who have a big global ocean buoy group. And we talked with them about what we wanted to do in the idea of how do we make this system so they can go on multiple platforms, not just the ones that we're used to. And so this just gets back to that this is a real team project. These are a couple of the platforms that we're interested in making this system for. The one on the left is the big WHOI buoy. This is the NSF Ocean Observatory Initiative. These buoys are spread globally. I think there's like 3 or 4 out in the open ocean globally, and then several in a coastal network. And then this is just an example of another moving platform that is making flux measurements and would like to make carbon dioxide flux measurements. This is a sail drone. I noticed they've changed their color from red to gray and black now. And I used to work with sail drone, but it seems like the company has changed somehow. I think they've gone to a military emphasis. And so from an engineering side, these were the kind of things that we discussed. This system has to be able to only take about 20 watts on 12 volts, which is for these buoy group guys, they were like 20 watts, we can give you 2, you know? And then, you know, for me, for most people, it's like you get a generator, you power it up, and so we get maximum 20 watts. And so a lot of this gets into just like, how do we do this? And we were able to get pretty close in the buoy we deployed before. We were at around 30 watts when we were full on. And so it's not out of the realm of possibility. And then the other point with these systems, especially on a buoy, to collect a lot of data to make that K model better, we're interested to be able to stay out for 6 months to a year with this system unattended and working. So these are the hoops that we're jumping through to make that happen. And so Sean is over there right now in our high bay over in Morse. He's there. Basically taking these different systems that we've tried to make improvements on over the last year and getting it ready. And we were hoping to go out in the water in 2 or 3 weeks, and we've got babies coming and people going on cruises, and I think it's gonna be like, I don't know. We don't like to put buoys out in December into January and February in the Gulf of Maine when it's the first time. So we may get in November into December, or we may be out there next March. But right now it's looking like we may not totally get there. But the pieces of the puzzle that we're working on, just to give you a quick run through, is just more of the same but better. So this is the new gas analyzer that Campbell spent about 16 months working on over the last 1.5 years with this improved detector. And this is just a quickie plot up on the top. Again, we're running a constant CO2 and detrending it. The red one is the new sensor with the change detector. The black one is the one they'll sell to you right now. And this is just with simple, just sitting there manipulating the sensor like this. And this is what, I can't believe people went out at sea and made measurements with these things for CO2, knowing that that was happening. And you go, oh, they go, oh yeah, it does, you know? But I guess the point was they're trying to motion correct it. So as long as they thought, as long as they could have, as long as they had a system measuring exactly how this was moving, then they figured they could correct it. But what was going on inside that little can was happening in a nonlinear way. So it turned out we were getting hysteresis, and we just couldn't figure out how to correct it. So that sensor arrived this summer, and it's been waiting for the rest of us to catch up. So this drying loop that we have to do, we basically have to dry the air before it gets down to here, because water vapor and carbon dioxide are coupled in an infrared measurement. So they're gas absorption measurements. So you're trying to measure how much your signal drops for the number of molecules of water you have in here and the and carbon dioxide. But they're both in the infrared spectrum across each other. So you have to correct for that, and that's another limitation to how well you can measure carbon dioxide. And the answer that people have come up with is just get rid of the water. So what we have to do is put a Nafion PermaPure drying loop in line with the air sample as it comes down from the top of the buoy. We have to extract enough water to dampen the water vapor perturbation signal so that it doesn't affect the carbon dioxide. And that's what's being done on a ship program. That plot is from Scott Miller on our program did a while ago. And these are results Mark and Sean did down at the pier at the Coastal Marine Lab with a 2-meter length Nafion tube and a 4-meter. So we've been just doing trade studies, trying to get as small as we can with these Nafions. And this is basically power and space trade assessment to get us drying that will support. And Sean did so much work, I just wanted to show a picture of where he was working down there at the pier. And this is a sonic anemometer and one of these intakes of the air where we were doing this comparative measurement between an open path and a closed path sensor like this to check this drying loop problem. The next problem is being taken care of by the guys out at SUNY Albany in Scott Miller's group. And we call this the sneeze. And this is a picture there. We had a camera on our buoy last time, and so we were taking a picture a few times an hour. And this is a case where water droplets are on the camera, which was on the top of the buoy. And we're getting wet, and sure enough, we would see that we would ingest water. And so we built our first version of the sneeze, and this is the air going into this intake that Campbell Scientific has built. It's a vortex intake. It rejects water naturally, and it does a good job. It almost gets rid of all of it. But when we get a lot of water, we start to get water in the sample line, in their bypass line. So what we have is a rather elaborate system where we use compressed air, and we blow it back up through the system as soon as we see water hit this thing within like less than 1/10 of a second. And that's what we call the sneeze. And we have a circuit to detect the water, and this has been an interesting engineering problem. We have a new student out at SUNY that's been working on optimizing this, Michael Jacques, and he's been doing a great job. But what we haven't figured out yet is an elegant way to get enough compressed air on the buoy for 6 to 12 months. And right now, what they came up with is a 50-inch long cylinder. It's going to be down there on the buoy. You see that sneeze cylinder? we're gonna strap something on there that, to me, it looks like a big horse blanket or something, across the bottom of the buoy that's gonna hold this air tank. And we've added a DC compressor. And we don't need very much air to reject the rain that's coming in or the sea spray that's coming in. But if it's raining a lot, we need to do it enough to keep it clean. So we have to have a control system built into our data acquisition and control so that we don't basically suck all the power off the buoy trying to run this compressor. But at the same time, we keep dry. And so right now we're trying to figure out how to shrink this. And if anybody is, knows a lot about, how to deal with compressed gas in a small tank and low power, please come and talk to me. And I think this is going to be something that we'll probably have one more iteration after this project. Campbell Scientific saw that we were using a sonic anemometer, and they were like, why are you doing that? So they built us a whole new anemometer, which is a vertically mounted. For our buoy, we need something that's vertical instead of side struts for the anemometer, which theirs typically looks like this. But structurally, and for these big ships, when you put a buoy off the side, you can ruin your sonic. These are pretty expensive systems, but if they're ruined, you're not making science either. And so trying to get a compromise between a sonic anemometer that we can deploy on these platforms, they went ahead and built us an all-new sonic anemometer that is custom built to take also that CO2 inlet on there. And this just arrived a couple of weeks ago, and we're working on integrating that onto the buoy right now. And so where is this all heading? We're basically gonna do it all over again. We're putting all this that we're putting together onto the buoy that you saw in the picture in the shed there a little bit earlier. We're gonna basically test this next iteration of our systems. And the idea is that a repackaging of them after we know what works and what doesn't work in terms of the power budgets is headed for a platform like this. And Campbell Scientific, and so this is an example of where these buoys are located. But Campbell Scientific is basically thinking about how to package this up in a commercial unit now, where they can get into a form factor that can go up on the top of one of these buoys. I don't know if you can get a sense of the scale or not, but hopefully you can. This is, we're only talking about something like 8 inches, 24 inches long for these kind of tubes that they have room for. And so the best outcome for our project so far has been how interested and how dedicated the Campbell Scientific people have been in terms of wanting to take what we're doing, thinking about it from their side, and they're basically trying to micro-miniaturize as much of this as they can in the version that they're looking to be able to sell by 2027. So with that, I can take some questions. Thank you for your attention.
Have you got a motion sensor built into the buoy does that affects the anemometer readings, I guess, the motion?
Absolutely, it's a fundamental part of the problem. So, or the solution, I guess, right there, that little GX5. Yeah, that's always a part of one of these systems. And in the case of Campbell, they're planning and wanting to build it right up into the top of the mast eventually. But there's power considerations on these too. We have a really beautiful one now, and Nathan uses it on his buoy. It's really power hungry. So we have to, there's trades that we need to make, but yes, quick answer. Another question back there? Or does that seem one?
As you've told other colleagues at universities, like what your improvements have been, is the reaction kind of like overjoyed that there's a better sensor, or people like, oh, I could have done that? Like,
well, at that meeting, we still couldn't tell them what it was. To be honest, I work across so many different fields that I haven't been to a carbon dioxide conference in a while. We published our papers, and I know they're being read, but I haven't called up my old friends that used to do this, because they don't do it anymore. But no, I can't say, I know that people are really excited, and they know that this is being done, and they keep calling both Scott and I, a few people, and saying, when can we buy one? And that was the most disappointing part about where we were a couple of years ago. We're like, I can't buy one either. So hopefully we will.
You come from the world of remote sensing where you're generally trying to estimate something over an entire surface. And I gather what you're doing with the buoys is that you'll get information for one point.
Yes.
And so I would assume you would have a natural tendency to say, well, how do we extend that beyond a certain area? When you think about the data that you're collecting, in order to do that type of thing, instead of having whatever it was, 12 or 15 points across the world, are you looking at linking remote sensing so that you can get a surface, or is that a consideration at all?
I think the idea is to get an adequate K model. Right? Once you have an adequate K model with an adequate parameterization, we're never going to know exactly the transfer rate anywhere in space or time. Then you can do whatever you want with, as long as you've got that delta PCO2 with its uncertainty and your K with its uncertainty, you can use remote sensing. A lot of people make a machine learning gas transfer model right now where they estimate the wind from a satellite, they put it into the K model. So, but in terms of eddy correlation flux, we're never going to be able to populate the world with these things. I'm not as ambitious as some people, so maybe I'm not giving you the answer that somebody else would give you. But I think the idea is that we're trying to create a large data set to be able to robustly test these K models. And to do that, I think it's more about statistics, because waves and wind decorrelate at fairly large spatial scales. So the wave height will be the same over 20 kilometers typically, unless you're in a real coastal region. So if you can get to a place where you build up a big enough data set and you've made the measurements of the controlling parameters well enough where we made the 20-minute measurement, then I think that my thought is you would be building that statistical data set, and then space and time, you start to make some assumptions. Thank you.
On the IOO buoy at the end there,
Yep.
there's two sort of turbines on that. Are those anemometers as well, or are those generating power?
That's just power.
Are you able to curb some of the power draw from your system here by using like a renewable energy source on the buoy itself, or is it still a really hefty draw?
You mean, where's the hefty draw from our system?
Yeah, for the instrumentation they're trying to run, that 50-watt draw there, are you able to?
Yeah, it depends on the engineer that's running the buoy, right? Because typically the idea is you're bringing a subsystem to them and you're telling them what you need, and they're telling you what you can't have. You know, so if they're flexible and saying, oh, actually, you know, we can give you this during this time of year when we have a lot of wind, and they've shown us plots of when the solar panels are charging and when the turbines are doing it. I think the turbines do 2/3 of the work on this buoy. So I have some plots of the power draw from that over time. But they were open to working with us, but each different customer is gonna have a different need, and so that's not a great answer.
No, that's okay. Sorry, I'm hogging the spotlight here. Are there other options that use other energy sources? Because I know there's a big push right now to do like triboelectrics or other forms of generating power via the wave motion. Or are those not really on the market yet?
That's not I don't know much about that.
Thank you.
Yeah, Nathan?
Yeah, great stuff. I'm glad that you can finally talk about this. It's exciting. The problem with the infrared detectors, is that going to be addressed across all Campbell ergas? So like, will the Ergason have an evacuated detector?
Yeah, no, I guess the thing I didn't bring up was that little detector I was just showing you is the reason they're using it is because it's cheap.
Yeah.
Right? So they can get those for like a couple $100, and people sell a lot of gas analyzers. And And so once they saw what we wanted, they're like, no, we're not gonna do that. Get a project funded by NSF. And so it's not like they're super expensive. We had to go to Teledyne, some place where they make this stuff over in New York, and we have special non-recurring engineering. But once they built it, I think that they could get down to maybe 2,000, 3,000 for one of those detectors. But it changes the price point and it changes marketing, right?
Because I know like purchasing a lot from Campbell, they love to give you options for customization, so,
That's the idea for this.
check a box and say, yeah, I'll spend $2,000 for the high sensitivity model.
Yeah, I think that's what they're thinking.
Okay, cool.
And, that's why they wanted to pass.
Because our latent flux heat measurements are definitely impacted by motion, and it's probably something similar, even though it's an open path system.
Yeah, water vapor is, as long as you have a lot of signal, then you can sort of correct out some of this stuff. Part of what carbon dioxide is, it's really small signal out there compared to like, you can do this, you'll probably put a buoy in the forest and move it around and measure the CO2 flux pretty good because there's so much carbon dioxide being exchanged. But over the ocean, it's minuscule. So that was part of the problem.
Another flux measurement method I've heard of is like the dual tracer with SO6 and helium. This is obviously a lot easier than that, but like how does it compare accuracy wise?
I don't know if it's easier.
Or I mean like if you could just buy one of those versus like having to.
Well, it's kind of what he was talking about with the spatial. This is a point measurement, so if you get in a room with these guys, I haven't been in there for 15 years, partially because they're very cutthroat with each other. That guy doesn't like the eddy correlation flux guy, and they almost get it, it was like, it used to be almost hostile. So each group really likes their method, and that was part of the reason that the eddy correlation was taking such a hit for so long in gas exchange. The other measurements, no, but in gas exchange, because of the sensor, was because the dual tracer guy said, we're much better. Ours works, yours doesn't. So I think depending on who is standing up here, they would say theirs is the best. But I think that they all work very hard and they all can defend their method as well as they can in their papers. Good scientists. Tom.
Yeah, so really interesting and makes my head hurt trying to understand how you can make these eddy correlation flux measurements. For years in our field, we were looking for sediment flux measurements, trying to measure velocities at a range of frequencies to very high frequencies and sediment concentration at the same time. Synchronize those and get them from the same volume. So the complaints were always, you're not measuring the same volume. You're measuring sediment concentration here, and nearby you're measuring velocity fluctuations. So for certain frequencies, that's not a problem with the length scales that span those distances. In your case, you're also sucking air in from an intake and taking it to that sensor where the measurement is made. Is there a filter, a mechanical filtering mechanism that occurs when that happens?
Yeah.
And that must impact the frequency range over which you're making your eddy correlation flux.
It does, and that's part of the trade-off with that dryer. That dryer is actually killing some signal.
That's right.
So the shorter it is, the less turbulence we kill. But we do have to live with the fact that we're in the highest frequency damping. But a large part of the signal, the majority of the signal is carried in lower frequencies that we believe we're in pretty good shape for. And then you'll see everybody has a little alpha term that they add on at the end to capture the frequency damping. I think the atmosphere is more forgiving than the bottom of the ocean in terms of the turbulence and what you can assume about it and how well behaved it is for at the kind of the 1 hertz out to say 0.02 hertz. This is the eddies are something like seconds, minute down to seconds or milliseconds. Those are the eddies we're after. And in the atmosphere, obviously, that's a lot easier.
So this was a 10 to 20 minute time series goes.
Yeah.
Okay.
So it's a noisy measurement even when it's made well.
Thank you.
So you referenced some measurements that were on the ship, the Ron Brown, I think.
Yep.
And they were trying to take out the motion there.
Yep.
And then you A lot of what you've talked about is the complications of putting these on a buoy with low power, and so are they gonna be building a ship instrument too, or is there a need for that? And
Oh, no, absolutely. This would be plug and play on a ship is the idea. Yeah,
you wouldn't have all the power complications there, right?
that's correct. That's correct. But I think in the end, if we can do it, I think that there aren't a lot of reasons why you would rig up your own if Campbell's willing to put this all together and it's adequate. Part of the thing that you do as a scientist is how well do you have to know what you're doing with the technology you're using. And I think the Campbell's idea is that they are good. I will say the engineers we're working with are really good. So they understand exactly what we're talking about and they know how they would do it best. And I'm excited that they're gonna try because I think it would be great to be able to put the same system on a ship, but yes, you're right.
And it could operate all the time on a ship?
Yeah, so for example, that sneeze would be much easier on a ship. We could just say, okay, and the way we're designing it is, we don't care where you get that air from, right? So on a ship, you get your air from a cylinder, which is what we did last time. We just strapped a air cylinder on the buoy and a regulator. And the thing was, we were only gonna be last for 2 months, and we were gonna be out of air. And so that's what you do on a ship.
Any other questions?
Well, thank you for being here. I know that you probably had to be here, but I'm glad that you came. And come over and see us in Morse Hall anytime you want.
We're glad you came here too.